Chapter 6, Number 19. Two springs with force constants given as K1 and K2 are connected in series, as shown in the figure. When a mass is hung from the springs, what is the amount of stretch X? So this is, as indicated, this is something called series spring, because it's one after the other. The other case, in number 15, for instance, are parallel springs, because they're side by side. And what we have to do here that's a little tricky is we have to figure out the tension in the strings themselves, or in the springs themselves. And so on one level, it's relatively straightforward. If we sort of put this as our box, then we have that spring, the box is being pulled down by gravity, as usual, and spring 2 is pulling it up. So this is, I'm just going to call it F2, but it's the force from spring 2. And at first you're like, oh, well, that's easy. And that lets me know how much spring 2 has stretched. And we just go through the sum of the forces in the y, which we can see from the diagram is F2 and Fg. But Fg points downward while F2 points upward. So one of them has to come as a minus, and I'm going to bring Fg in as a minus. And we know that from the second law, that has to equal ma, which is 0. Now we know that F2 is coming from a spring, so F2 is going to be the spring constant 2 times however much 2 has stretched. So in essence, by saying this, we said that 2 stretches down by some amount, which I'm going to call x2. And then at the same time, 1 is going to come down, and we're going to figure that one out separately. But this one's pretty easy to do because we see from here that tells us that K2 x2 minus mg is 0, or x2 is mg over K2, which is 0.90 kilograms times 9.81 meters per second square, all over 250 newtons per meter, a total distance of 0.0353 meters. I'm going to keep one extra decimal place because eventually we'll need to combine this with something else. All right. But that doesn't tell me much about what happened with spring 1, because what really goes on, of course, is that spring 1 stretches by some amount. So we start with this, and spring 1 stretches by some amount I'm calling x1, and then spring 2 stretches by some other amount, and we'll call that x2. And we want to know how much x1 is, because the stretch of x1 plus the stretch in x2 is how much this point has moved, which is what we're looking for, because it's the same as how much that point has moved. In other words, we're saying this is also x, and the motion of this point is clearly x1 plus x2. The tricky bit is, how do I get x1? And the way I get x1 is I play a little bit of a trick here, and I say, let's consider the thing connecting spring 1 to spring 2. And that thing has a downward force from spring 2, because spring 2 is trying to compress, so it exerts a tension at either end to shrink the spring. And that's maybe the most important thing. The tension in a spring, or the tension in a string, or whatever, acts at both ends so as to shrink it. By the same logic, spring 1 is pulling upward so as to shrink its length at either end, and so that point of juncture, the connector between the two, is being pulled up by spring 1, but it's being pulled down by spring 2. We can basically assume that it is massless, that is really, really tiny mass, and so although technically there probably should be some tiny little Fg prime or something, it really would be absolutely tiny, because we're talking about a thing which is of really arbitrarily small mass. We can make it as tiny as we want. So in that case, we don't worry about it, and so we have that the sum of the forces on the connector, which is F1 minus F2, is also 0, which means that F1 has to equal F2. But F1 we know is equal to K1 X1. So that has to equal F2, and F2 was equal to mg. So X1 has to be mg over K1, or 0.90 kilogram times 9.81 meter per second square, all over 150 newtons per meter, and that turns out to be 0.0589 meters to 3 decimal places. I have not done a great job with board space, so I'm going to create a thing in the middle to finish up with this. And I'm going to say, oh, well, at the end, the actual distance x is just x1 plus x2. In other words, the amount that the blue dot moved is just how much the first spring stretched plus how much the second spring stretched. And so that's going to be 0.0353 meters plus 0.0589 meters, which turns out to be 0.0942 meters, which we really only have 2 sig figs, so it's going to be 0.094 meters, which is the same as 9.4 centimeters, which the back of your book gives as the answer. So what we get here is, in essence, the stretch is weird because it's the sum of the 2 stretches, not any one directly. This is sort of a general result for series, and we're not going to delve into it at the moment, but it adds in sort of an unusual way.